Hi, good morning, everybody. My name's Hayden Povey, CEO of SCI, as you can see. And our project was slightly different in that it was very focused on the CHERI implementation and how we started to bring this to market. So I'm up here presenting. I've also got David in the audience who hopefully can pull me out of any technical issues that I get into. Okay, so one of the things that we want to do with CHERI in general is look at how we can start to commercialize the technology. It's a fantastic concept, but it has philosophical impacts, how people write their software and how they get to market, the devices that they use and so on. So we were really looking at how we create some stepping stones in there. And for those who don't know me, I was at ARM for, well, over a decade. I was the originator of the Cortex-M cores for microcontrollers. And then no good deed ever goes unpunished. So then I was given all of the security technologies. So working with Apple on Apple Pay and Samsung Knox and those types of technologies. So I don't think there's many people in the room, probably in the industry, who have had that experience of both embedded systems and security. But please don't blame me for TrustZone for Cortex-M. One of the challenges that we really see in this area as well is a lot of the embedded environment, they don't use C++, they don't use modern C. They still use very legacy C instructions. For the last 5 years, I was Chief Strategy Officer at IAR, who are a compiler, an IDE vendor. And the reality is, you know, with microcontrollers from ST, from NXP, from Renesas, whomever, these guys don't move very quickly. They're very, very conservative. So how do you bring the two ends of this story together? How do you take new technologies like CHERI and CHERI and actually start to get that into the hands of people who are building real-world systems? And that's what we're trying to do with SCI, and that's what we were trying to do with this project. How do we create the stepping stones to creating next-generation secured microcontrollers with proper IP enforcement? So when we think about CHERI, when we think about compartments, obviously there's lots of different use modes, but the biggest one which I found out there is third-party software and microcontrollers. In many systems, and I worked on the Indian Aadhaar project, if anybody knows that, which is around how do you secure banking in a country like India based on iris scans or fingerprint scans. How do you implement that in a low-cost system and a bank on a back street in a supermarket? And while there's lots of tech information systems out there, the guys who license that software don't want it to be open to the rest of the system. They need to contain it. So things like IP enforcement and management of libraries at a commercial level is really important and a very different use case than what we traditionally see in the CHERI domain. We need to do things like SBOMs, the software bill of materials, of course. We need to know what's in our system, but we need to enable and envision a much wider ecosystem in the embedded world. Something akin to the rich operating system environment, but done differently. So we were able to leverage CHERI, obviously from Microsoft, as a framework for this and fundamentally get that operating now on the FPGA platform and move from a lot of the theoretical implementations to real world implementations and try and make that work, break it and take it forward. So we started off, and actually the project we pitched wasn't with FreeRTOS, it was with Azure RTOS, which is the Microsoft version. It used to be ThreadX. Unfortunately, we came up with a number of licensing issues. By a freak of good timing, that got solved yesterday. Microsoft have now republished Azure RTOS as ThreadX with a permissive license. I don't know if we're to blame for that or not, but it's nice for them to bring that back into the marketplace as ThreadX. Billions of users of ThreadX, billions of users also of FreeRTOS, which is the AWS implementation. We wanted to take it from sale and start using it with some level of reality, with some level of higher frequency running on the FPGA. And actually, this is where most of our project effort actually went. There is a unfortunate reality that there's a big difference between not the Chariot core, but the system operating on SAIL versus operating on the FPGA. So the core, I think, is pretty, all the software on the core is ported very well, but we found things like undocumented UART communications. It just didn't work. And unfortunately, a lot of work had to go into that. So we wanted to use that, as I say, to create the stepping stone from FreeRTOS running on a Cortex-M, so standard STM32L4, pretty vanilla, pretty mainstream, excellent product, but it's kind of there as a state of the art. We've moved it to FreeRTOS running on IBEX as an initial RISC-V implementation, and then moving FreeRTOS to Chariot, and then ultimately looking at what David and the team at Microsoft have done running Chariot RTOS on Chariot and how we can bring the ends of that together. Because the reality is a lot of our users are not C++, certainly not C++20 users. The outcome of the project has really been around how we document that story, how we enable the industry to move forward. And again, David's done a fabulous job around documentation, and we'll talk about that in a little while. So project components, there was actually quite a few feed-ins. Obviously, ARM and the AWS ecosystem, the Morello board, and the work that Hesham had done around the original FreeRTOS port to Cheri. At the bottom, Cheri itself and SAIL, moving that onto Chariot Safe. Again, this came out just at the right time for us. We were able to leverage it and work with the Microsoft team to get that implemented properly. And then the gray area is really the work that we've been doing. So most of this has been done. We've still got some work to complete around the full free on Chariot, but we're continuing that on anyway. And then the portability. In terms of effort, not surprisingly, the FPGA took most of it. It was about 30% of the project. The actual porting of Chariot RTOS to use the correct peripherals, timer counters, and things along those lines, about 20%, and the same for the other areas. Current status, most of it's done. Still a bit to go on around the FreeRTOS on Chariot Safe and the white paper, but we're doing pretty well and continuing. The documentation started off as a white paper. It's turning into a pretty thorough book. And again, David and others have done a great job with, as you can see here, porting from FreeRTOS to Chariot, and the implementation and use cases of CHERI in a microcontroller domain versus porting from bare metal. So there is a draft of that available on CHERI.org. Yeah. So we'll point to that out there. This is an implementation that we have for the RISC-V system with the FreeRTOS core, the BSP underneath that. And again, it was probably about a third to get this working. The BSP took an awful lot of effort to just get it working, not surprisingly. The core, some effort, and then the application sat on top of that, and trying to bring that to bear. The CHERI RTOS implementation, as we say, this runs on the Xilinx Artix, right now the RTA7 board. We've actually got a demo here, which we can have at the back, demonstrating how we can load code, how we can demonstrate against secrets being leaked and attacks operating in that with some JavaScript. Some of you may have seen that previously, and there's a video that we submitted around that as well. Is this going to work? Here we are. So this is the video. We can load firmware without compartmentalization, or with it with compartmentalization here. You can see at the top the secret was very simply leaked, whereas at the bottom the secret has been protected by the compartment boundary. So we're proving in real-world embedded systems that the system works. Similarly, we can try and crash the system at the top. Crashes, not surprisingly, at the bottom. The crash is isolated inside the compartment. So again, these are real-world use cases that we're demonstrating, which are executing on pretty much real hardware. And again, you can just see a few blinking LEDs, and if we can get the LEDs blinking, we can do anything. Okay, so challenges. I know I'm over time. The CHERI at Safe implementation was a challenge because of the nature of the system. The core, fantastic. The system, challenging. There are other challenges here around, we're very used in microcontrollers to the CM/sys abstraction layers on ARM. There's no equivalent on RISC-V right now. There is some work being done in that area, but it's behind the curve. Again, on the RISC-V implementation, just a lot of challenges. Some differences between the CHERI RTOS working on SAIL versus working on SAFE. And again, not really the processor, more the system. I think the other big one for me was actually resourcing. Finding people who knew embedded systems, but then were able to take on CHERI and Chariot was actually quite challenging and quite frustrating. We had a couple of false starts on that before we really got to the right person. We've also obviously got David joining us, but it is that learning curve, which is going to be the biggest challenge to the industry. How do we make it simple to consume this technology? How do we make portability easy? Because in embedded systems, really you don't have hybrid, it's pure cap. Everything's going to have to be recompiled, everything's going to be rewritten. It's fine because it's embedded, but as Chris was talking about earlier, you have to have high reliability systems, and you have to understand what's executing on your system at all times. So a number of challenges there, but I think we've gone through those pretty well. It's been a great project for us to demonstrate CHERI on the FPGA, and I think we're in a great place to now move that forward and to commercialize it inside a slightly larger system. And certainly over the next 12 months or so, we'll be looking to get some silicon to the marketplace. Okay, sorry, I've gone over.
Thank you very much.
Any questions?
Yeah, any questions for Hayden? Do stick your hand up, and we can get a microphone round to you.
Hi, thanks for the presentation. I was just wondering if you could, are you able to comment any more on your plans for silicon? Because silicon in 12 months sounds, well, quite quick.
Yes, we're obviously leveraging the Chariot core and some other pre-existing IP. And our key differentiation is really around the memory system implementation, but I can't, in an open forum, go into that further, but I'm happy to talk to people individually beyond that. Obviously we'll be doing microcontrollers, so we're limited by non-volatile memory. So we're not going to be in 5 nanometers. Again, my personal background, having led Cortex M3 when it was still Sandcat, if anybody's aware of that. We worked very closely with ST, Broadcom, Luminary Micro back in the day to get silicon into the marketplace to purposely go and create an inflection point. At that point, ARM had some 70 DMI microcontrollers out with NXP, but weren't really in that marketplace. And I think we did a great job at creating that market and challenging people there. We hope to be able to do the same again. Obviously, right now, there's no CHERI-based ARM hardware. So, sorry, Mark, it is RISC-V. So,
thank you. How critical is the CHERI extension on RISC-V standardization process? How critical is that to you?
Somewhat. I think as an early adopter, an early mover, we can create our own environment. We will be able to bring in commercial tools because of our relationships. And I've been running most of IAR for the last 5 years. But obviously standardization is important. And we do want to work with our partners in academia and in industry to standardize the extensions around RV32 especially.